Hello everyone. So welcome back to physics classes. Okay. So today we will be starting or we're just doing the series of quick revision for the board examinations 2024, 24 and 25. Okay. So for the class 10th ICSE. Okay. It's a complete revision of that chapter. Okay. So one by one we'll be finishing this each and every chapter and you will go through each and every topic. So after that you don't have to read any of the questions or nothing or any book. Okay. So it will be covering all the concepts thoroughly. Okay. And just after that, the notes of this chapter will be at the descriptions. Okay. And if you want the practice paper or something like that, just kindly join that particular Telegram link and I will just share you with you all. Okay. So here we go. Yeah. So this chapter name is radioactivity. Okay. So now let's see here. What we can see here is right now. So, yes. So we are talking about the atoms. Okay. So this is a basic concept and we will be going a little bit quick. Okay. So no need to worry about here. Okay. So this atoms. So basically atom structure everyone knows. Okay. Now when we talk about the atoms contains the nucleus and the electron which has been orbiting around the nucleus in a particular shell. Okay. In each orbit we can say. So now nucleus contains the nucleons and nucleons is further divided into two parts. One is the proton, another is the neutron. Okay, when we talked about the charge on the protons and neutrons, so neutron is neutrally charged, but the proton is positively charged, containing 1.6 into 10 power minus 19 coulomb of charge. Okay, when we talk about its mass value, so mass is 1.67 into 10 power minus 27 kg. Okay, it's kilogram. Now, for the neutron do not have the charge, but it has the mass that is 1.6754 into 10 power minus 27. That is slightly heavier than the proton. Okay, that is the mass of the neutron is slightly heavier than the proton mass. Okay, so this thing I think everyone knows it well. Okay, so keep remembering this one part. Now, let's go with the next slide. Here we all the mass that concentrate. Let me just put it somewhere here. Yes, all the masses of that is concentrated at the center of the atom. That means the whole mass. This we have already studied in the chemistry one part in the Rutherford atomic alpha scattering experiment. Okay, now all the mass of that atom is being concentrated at the center of it, and that is named as the nucleus. Okay, then element having the atomic masses and number of neutrons. So if the atomic mass and number of neutrons is increasing, that element means it's a heavy. Okay, getting it? Now, in the BEC, what is BEC? It's a binding energy curve diagram in which iron is most stable. And after that, when we go for, so it become instability starts to come. That means after 90, number of neutrons is increasing. So stability become, or the we can say it's become unstable. And to get that particular element to get it stabilized, because in this universe, everything needs to be stabilized. So if they want to get stabilized, so what they do, they starts to radiate. They start to radiate. And what they radiate? They radiate the radioactive particle like alpha, beta, and gamma. And from there, we got to know about the radioactivity. I hope it's been clear to everyone. Now let's go to the next one. So, like uranium, polonium, etc., and thorium. These are the different radioactive material. Now, coming to the part of the theory where's the Dalton's theory. So, atom is a tiny particle, he said, which is indestructible. You already know about this, okay? But it is wrong because atom has very all small particles like electron, proton, neutron. It has, okay, it's not only the atom. When we just segregate it, so it becomes electron, proton, and neutron. And then also this electron, we have the subatomic particles like quarks, okay, up quark, down quark, okay, meson, pi meson, like this. Now, then J.J. Thomson come into the picture and he gives the plum pudding model or the watermelon model. Okay. So in this, what he told, let's take an example of watermelon, cut it into the half in the two hemispherical shape. So what you will find, the red color of the edible part of the red color is the proton, and this black seeds are been working as a electron. That means the electrons is being distributed all over the area in the proton itself. Okay, so this we are believing it. But later on, what happens? Then the Rutherford come, and the Rutherford have the two students, okay, who just use we work under the Rutherford, and that was Grigor and Marsden. Okay, so they performed the alpha scattering particle. On the alpha scattering particle, what they have seen, they observed many times. Okay, but the one main thing has been coming to them. That is what they have put it the bismuth material. So you need to know about the bismuth is the radioactive material which is they have put it in the lead box. Okay, it's a alpha particle plus 2 charge it has. Then for this they have the collimators here so that the radiation won't go here and there, just be have the straight path for going. Then they have put it a very thin gold foil, very thin gold foil. That means seems to be a transparent sort of. Okay, being it's a metal or the opaque, but it's been so thin that it seems to be a transparent or translucent sort of the things. Then they have the circular disc, as you can see, a circular disc, and there they have put it the microscope, okay, which is used to rotate here. Okay, so I have this is you already read it. Okay, the main point which is you have to remember is now this screen is being coated with the ZnSO4, that is zinc sulfate, and this is a gold. So whenever this alpha particle going to strike, so it just emit some radiations or some emit some electrons from there, and when it strikes the surface it starts to show the scintillations. Okay, a sharp sparkling thing. So this we can say a spark there, and there we put the microscope and we find the angle from them. Okay, now J.J. Thomson is correct. Alpha particle is plus 2 charge. Okay. And this is what gold, that is having the plus Ze charge, atomic number in charge. Okay. Now, but the thing is actually the J.J. Thomson is correct? No. We were thinking he's correct, but he's not. Okay. Because while doing the alpha scattering particle, one thing we got to know about it, that's what? If the number of charges we are finding it, for example, C. I know you already studied this one part, but let me just explain it again. If suppose this is a complete positive charge, we can say the complete positive charge having just some electrons like this only. And when we are throwing this positive charge, it won't go because this hole is positively charged now. But then also what we have seen, that we have seen most of the time we have seen the deflection, and the one which has been going there, either they passing through it. That means that the space is there lots. But out of this thousands or something, only the one particle is there which is going and then coming back. This made the whole theory here. Okay. The what was there in the mid, due to which what is happening? This positive charge is reversing back. So there must be some very high positively charged, dense positive charge, which is repulsing this positive charge. Yes or no? So from here the theory comes. So there is something, okay, at the center of the atom where the whole mass is concentrated, and then they named it as a nucleus. See, I'm not going into the deep of this one part because you already know it. Yeah, if you find any difficulties in any of the topic, so I'll explain or make the separate video of it. Okay, so you just need to put it in the comments. Okay, rest don't be just like this. I'm giving the short form because see, it's a quick revision video. That's why. Okay, so now, and when we find is the cycles of the nucleus, so size of the nucleus is 10 power minus 15, and the size of the atom is 10 to the power minus 10. It's a very small. Okay, but the thing is, how much is small it is? So they got to find out. Just like suppose if we are more talking about the field area of a circumference of a football. Okay, so what is happening? So in which if we keep some football in the mid of the whole field, and this is the circumference of the complete field, so that is the space between them. That is what the structure of atoms is having approximately. So nucleus one size is very small, and the orbit, first orbit, is very far away from here. So most of the space between them is empty. Okay, is empty, but this nucleus contain very high positively charged into it. Okay, I hope it's been clear. Now just the football one ground I have written. Okay, it's an empty circumference of the football ground and is the first orbit of the atom. Football is so football. So this is the size of the nucleus. I hope it's been clear. That is the size you can remember, 9 power minus 15 and 10 power minus 10. Then Neil Bohr came. Okay, so what he just explained. Wait a second. Yes. So Neil Bohr just came and he talked about the orbits like KLM and Shell. Then Chadwick came and talked about the neutron. See, you don't have to go for this, all these things, as you need to know about the things in a very short manner. So this in the question arises from this topic, you can easily give because nothing is going to be coming from this part a lot. Okay, the basic things will be asking if they come. So you can just easily give the answer. Like now, how you can remember the name? So there's a trick called eat per notch. Okay. So where ET is electron, T is Thomson. That means electron discovered by J.J. Thomson. Then P is proton. Proton is being discovered by Rutherford. N is neutron. Neutron is being discovered by Chadwick. Okay. That's a trick you can remember how who has found or discovered the particular thing. Now, neutron is a neutral and no charge, but it has a mass. Okay, so there is a thing which you are going to study in class 12 of the one of the property of the charge, and that is what if a body have a it's a see, it is mandatory. If a body is having a charge, then it must be having the mass also. It's mandatory, but it is not mandatory that the body is having the mass, so it should have the charge also. For example, neutron. If you talk about the neutron, neutron is neutral, but it has a mass. But if you talk about any of the thing which is having the mass, or we can say anything which is having the charge, it do not have the mass, that will be wrong, because anything which is existing here should be having the mass. Okay, not going to the part of the photons and all radiations one, that there's a massless particles. Okay, now coming to the element. So how we define the elements? These elements are like the element symbol will be here. This is being denoted by the atomic mass or the mass number, and this is the atomic number. Okay, so any represent you can go for like this one or this representation. Now Z is the atomic number, which is equals to number of proton, which is equals to number of electron. This is important because sometimes they may going to ask you how many number of protons, electron, neutrons has been there in a particular element. Okay, so Z is important. Okay, this how to find the Z, or what is to find the number. Then the atomic mass is also one. That is the mass number, atomic number. So it is number of protons plus number of neutrons. That means Z plus N. Okay. See, this is important. This one slide is important for everyone. Okay. Now coming to the number of neutrons. So number of neutrons is the atomic mass minus atomic number. This one is also important. Okay. Now let's come to the part of the isotopes, isobars, and isotones. So now coming to the isotopes and isobars, there's a stationary orbit also. Okay. So just remember the stationary orbit. What this stationary orbit is, it's a non-radiating fixed orbit. Okay, it's a non-radiating fixed orbit that's called to be stationary orbit. Okay, then there are k element shells are there according to Neil Bohr. Okay, so maximum number of electron in an orbit that can lies is will be 2, 8, 8, 18, 18, 32, 32. Okay, so that can be 2, 8, 18, 32. Like this k element shell we used to segregate. Okay, like in the first shell only 2 will come, second 8, then 18. So this you already studied in the chemistry. That's why I'm not going much into deep into it. If you find any difficulties in any of the part, just write the topic name in the comments and I'll just look into it, this one part. Okay. So size of the atom, this you have done. What is nucleus, proton, neutrons, atomic number, mass number, isotope, isomers. So let's come to the isotopes one part. Okay. So what is isotopes? Okay. What is isotopes? So isotopes are the one who's having the atomic number same. Okay. And mass numbers are different. Okay, so when we can see the example of hydrogen here, hydrogen having 1H1, 1H2, 1H3. Okay, so what is this is 1H3 now. This is 1H3. Okay, this is 1H1, 1H2, and 1H3. So what this means, it's a see, you can see this is the atomic number. So atomic numbers are same 111, but the atomic masses are different. Atomic masses are different. Okay, atomic masses are different. So for this, what we can see for the trick, what we can remember the trick here for this is what isotopes. That is top is coming means the top. That means top one part is changing. Just remember the trick as a this top part is changing. Isotope means top part is changing. Top part changing means 1, 2, 3. That has been changing here. Okay, it's a 1H2. Just a second. Yeah, it's a 1H2. Okay, shall. Then let's go for the different one, isobars. Bars means we can say go for the base one part. So base means base may we have the atomic C. If we are this is the element, this is Z and this is A. So top means atomic mass and base bar means atomic sorry, yes, atomic number. So atomic number is different, but atomic mass is same, like the calcium and argon. So calcium is 20 by 40 and argon is 18 by 40. That means 40, 40 is same, but the atomic number is being different. I hope this much is being clear to everyone. Yes, isotopes and isobars. It's an important slide. Okay, guys. Let's go for the next isotones. Now here another thing. So it has the different atomic number, different atomic masses, but the same number of neutrons, Okay. It have both the things different. Atomic number also different. Atomic mass is also different. That means for the isotones, we have A is different, Z different, but it has number of neutrons same. Okay, it has number of neutrons same. Okay, I hope it's been clear to everyone. Now there is an important note for everyone. Okay, for this what we can do, if an atom, see, these important notes are very important for us, cause from them the, we can say, assertion reasons, logical questions can come. Okay, so if an atom undergoes the chemical change, then number of orbital electron changes. Remember this one part. If an atom undergoes the chemical change, if atom is going under the chemical change, then the, just a second, let me just change the color. Yes. So orbital electron changes. Just go for this one. Listen this first. Atom undergoes chemical change. If there is a chemical change, it goes for orbital electron changes number of. But if the atom undergoes the nuclear change, the number of nucleons of an atom changes. Number of nucleons changes. Chemical reaction related to electron, nuclear change related to the nucleons. I hope it's been clear. It's the important part. Now, coming to the nuclear charge, next one important point, for the nuclear change, we require energy in order of some mega electron volts. This MeV is mega electron volts. Okay, that's a unit of energy. Okay. Okay, so for the nuclear change, we require some energy to do it. Okay, so mega electron volt is 10 to the power 6. Mega means 10 to the power 6. It's a unit of energy. For chemical, we require some change. Sorry, we can, for the chemical change, we require some few electron volts of energy only. Okay, see, so for the nuclear change, we require mega electron volt. And for the chemical change, you just require the electron volt of energy. Okay, now let's see an example, next important point. So here's the reaction has been given of a uranium. Okay, when the neutron is been bombarded on it. Okay, so it becomes like, what are the changes there? Because what we have done, we have provided some change into it. Okay, we have added the neutron into the uranium itself. So this is the atomic number, this is atomic mass, and we have added one neutron into it because neutron do not have any charge, so it's zero. It has the mass, so it is the, sorry, yes, it do not have the charge and it has the mass, so that's why it becomes 0, 1 by neutron. So when this has been added, it cannot hold for a long period of time, so it gets splitted into the barium and krypton, and it also emit the 3 neutrons again and a tremendous amounts of energy. So this one part is the reactant part, this is the nuclear change, and the last one is the product. I hope it's been clear to everyone. So the same example I have been written here also. Uranium 92 to 3501, okay? This is a reactant. So see, the Z is 92, atomic mass is 235. Okay, now atomic mass is 235. When the neutron is being added, so it will be added into the atomic mass, so it becomes 236. See, so it becomes 236.92. Same. Now, when it's been just goes to the breaking point. So what happened? This 92 starts to break into the 56 plus 36. So if you're just going to add it, 56 plus 36, that will be 12, and 5, 6, 3, 9. That is 92 came again. And when 144 and plus 89. Okay. And this is 3 into this one. So basically just add this one out. Okay. So you'll be getting this 235 only. Okay. Getting my point. So this is the, what it's follow the law of conservation of mass or law of conservation of energy too. So let's go with the next one. Yeah, okay. So during the nuclear change, see, I'm going a little bit fast, I know, but it will give you the quick revision of it. Okay. Maybe 2 or 3 videos will be there for the same topic because I don't want to extend for a long period of time. Okay. Let's see. So during the nuclear change, sum of atomic number of the reactant, sum of the atomic number of reactant is equals to the sum of atomic number of the product. Just remember this formula during the nuclear change. What is happening? Atomic number of the reactant is equals to the atomic number of the product. Or we can say sum of the mass number of reactant upon the sum of the mass number of product. Both the conditions can be satisfied. Now, what is nuclear energy? Nuclear is means part of the nuclear fission and nuclear fusion. Okay, when there will be change in the nucleus, so it just emit out the energy that is called to be nuclear fission and nuclear fusion. So what is the nuclear fission? If we take a heavy element, okay, and when it's split or break down into two lighter nuclei or lighter animals, so it just emit the large amount of energy, and this is the condition of atom bomb, and that to be the uncontrolled one. Uncontrolled. We are going to read that also. Now, in the fusion, two lighter nuclei got merged into each other and formed the heavy one, and it also formed very high amount of energy. Now, because why it's been there? See, if it is H and it is S, both are having the same charges on it, a positive, positive, and it's very difficult to bring the positive. Like for example, if you have north and south pole of the magnet, and you want to bring both of them very close. If the power is very less, then you can just hold it by your hands by putting the force from the external force. But if there's going to be the neodymium magnets, okay, so what will you do? Will you be able to make it more close? No, because there is very stronger field it has. Okay, so similarly, the two hydrogen is very difficult to just combine. So for that, we need to increase the pressure and need to increase the temperature, and then only it can form. Okay, so this is a hydrogen bomb, we can say. Now let's go for the next. So here again, the isotopes I have given with the proper examples and everything. So chemical properties remain same. Now see, for the isotopes, chemical properties remain same because of same atomic number. Okay, because atomic number says the chemical properties will remain same. Hydrogen is three isotopes. There is one H1, no neutron. That is ordinary hydrogen, most abundant and maximum quantity it is being present on the earth. Now one H2 is the deuterium. It has one neutron. Okay, it's a deuterium. It has the one neutron, one proton, and one electron. Okay, heavy hydrogen reaction it is. One H3 is the tritium. It's two neutrons, one proton, and one electron. Okay, so this is a very, we can say, like for example, it's very explosive. Okay, this one, two, and this very reactive also. So this the experiment, maybe you have done it or not, but if you just put zinc into the sulfuric acid solution, so it starts to emit some bubble and start to emit some gas. So what we do, if we bring the burning matchstick in front of this gas, so what happened, it just got fire, catches the fire and make the pop-up sound. Okay, because it's a hydrogen. So for determining what is between hydrogen or whether the gas is hydrogen or not, just bring the burning flame near to it, but in a very proper manner. Okay, so it will start to burn, and once it start to burning, that means it's a hydrogen gas. Now let's go with the next one. So these are the isotopes of hydrogen. We can go and see it. Then carbon. Carbon has the three isotopes. Okay, that is C612, C say 6C13, 6C14. So that is also an isotopes only. Outermost orbit number of electron is 6. That is 6, but it is 6, 7, and 8. It is also most abundant. Which one? C612. Okay. Now we have the chlorine. Chlorine is 17Cl, 17Cl, 37, 35. So this is the same. What is the ratio? Abundance, the ratio of 3:1. So you can go through these all each and every topic again. Okay, I'm just giving you the overview, which is need to be the defining one. Then 10, that is the SN, strontium. So largest number of isotopes is 10. Okay, so it is the 10 isotopes. Okay, the isotopes is stable isotopes. We have stable and unstable isotopes. If we have the stable isotopes, no issues. But if we have the unstable isotopes, they want to go for the stability. And when they go for the stability, they starts to emit or decay. And when they decay or emit, they are called to be radioactive. Simple as that. Okay, so stable isotope number of neutrons is almost similar or approx equals to number of protons in the nucleus. But for the unstable, number of neutron is not equal to the number of neutrons. Or basically, we can say number of neutrons is greater than the number of proton. If the number of neutron is more than the number of proton, then the material is said to be the isotopes. Oh, sorry, unstable isotopes. Then, so the material become radioactive and widely be used in the industrial and the medicinal uses. Okay, so in the next video, we'll be starting with the radioactivity. Okay, I hope you have been clear. And if you are just getting the things, okay, just revise it from the book or revise it from this only. And if you want the short notes of it or the same notes, so I'll be just sending, just put me, drop some comments or just go to and join this Telegram channel also. Okay, bye everyone.